Welcome to the third part of thermodynamics, and in this part you will learn how internal energy is different from heat and work and about first law of thermodynamics. Two different modes to change internal energy are heat and work. Consider a bottle and a balloon which is tied at the neck of the bottle. When we heat the bottle, due to the temperature difference, heat flow takes place and as a result balloon blows up. That is due to transfer of heat, kinetic energy and potential energy changes from bottle to balloon, and this results in the change of internal energy. Now consider the system. A bottle with a balloon tied. We can do some work on the system. As a result, the internal energy of the system changes. Internal energy increases when the system absorbs heat and some work is done on the system. Similarly, internal energy decreases if we change the conditions. Now, how internal energy is different from work and heat? Heat is certainly energy, but it is the energy in transit. A statement like a gas in a given state has a certain amount of heat is as meaningless as the statement that a gas in a given state has a certain amount of work. In contrast, you should say a gas in a given state has a certain amount of internal energy. And similarly, the statements a certain amount of heat is supplied to the system or a certain amount of work was done by the system are perfectly meaningful. Heat and work are not state variables unlike internal energy. These are modes of energy transfer to system resulting in the change in internal energy, which is a state variable. To understand it, consider the system to be a certain mass of gas contained in a cylinder with a movable piston. Here in diagram A, heat is energy transfer due to temperature difference between the system and the surroundings. And in part B of the figure, work is energy transfer brought about by means that do not involve such a temperature difference. For example, moving the piston by raising or lowering system some weight connected to it. There are two ways of changing the state of gas and hence its internal energy. One way is to put the cylinder in contact with a body at a higher temperature than that of the gas. And the temperature difference will cause a flow of energy from hotter to lower one, means towards the gas, thus increasing the internal energy of the gas. And the other way is to push the piston down, means you have to do work on the system, which again results in increasing the internal energy of the gas. Of course, both things could happen in the reverse direction. With surrounding at a low temperature, heat would flow from the gas to the surrounding. And likewise, the gas could push the piston up and do work on the surrounding. So in short, you can say that heat and work are two different modes of altering the state of a thermodynamic system and changing its internal energy. Sign conventions to be used for heat, work and internal energy to solve the numerical problems is heat absorbed by the system is taken as positive, whereas given out by a system will be negative. Work done by the system is positive and work done on the system will be negative. Increase in internal energy of the system, we will take it as positive, and for the decrease in internal energy of the system, it will be negative. First law of thermodynamics. It states that the change in the internal energy of a closed system is equal to the amount of heat supplied to the system minus the amount of work done by the system on the surroundings. Mathematically, if delta Q denotes the heat supplied to the system by the surroundings, delta W work done by the system on the surroundings, and delta U the change in internal energy of the system, then from the general principle of conservation of energy, we can say that delta Q must be equals to delta U plus delta W. And this equation is the mathematical form of first law of thermodynamics. It is simply the general law of conservation of energy applied to any system in which the energy transfer from or to the surroundings is taken into account. Let's put equation 1 in alternative form. Delta Q minus delta W equals to delta U. Now the system may go from an initial state to final state in a number of ways. You can keep the volume constant first and then keep the pressure constant, or vice versa. Since delta U is a state variable, means it depends only on the initial and final states and not on the path taken by the gas to go from one to another. But delta Q and delta W depend on the path. From first law of thermodynamics, delta Q minus delta W is equals to delta U, path independent quantity. That means if a system is taken through a process in which delta U is 0, means delta Q will be equals to delta W, and the heat supplied to the system is used up entirely by the system in doing work on the environment. If the system is a gas in a cylinder with a movable piston, the gas in moving the piston does work. And we can write the work done as force into displacement and replace force by pressure into area, and you will get delta W equals to P delta V. So by changing the delta W by P delta V in equation 1, you will get delta Q is equals to delta U plus P delta V.